Before starting, you probably have received this morning the latest slides. Um, there have been a few things touched up. I touched up those slides a bit this morning, so they're not exactly all of them the same as you receive, but it's pretty much the same. Um, I will ask Anirban to post the final set of slides. Now, he suggested, I think it is a good idea, that I make you aware of the examples that can be found in the code distribution and in the book. Um, some of these examples you are the ones that we have been working on, or at least subsections of these examples. Some of them have several subsections. But for you to have an idea, these are the subjects that are simulated and discussed in the chapter 6 of the book, and that you have in the distribution version of the code. So eventually you will receive this file or this updated lecture notes. So let's go to today's lecture. Okay, yesterday we ended up with example 3, location density with reversals. There was an issue with running the single crystal file, a constitutive law. We looked a bit at that problem today with Anirban. It seems to be a problem with the Windows 11 system. People running the Windows 10 system apparently didn't have the problem. We played a bit with that, and we don't know what is going on. So there was at some point it got stuck trying to read a variable, and it said that the type of variable was not correct, was not a real, although what is in the file is a real, and we don't know what is going on. So once we find out, we will try to send an email and tell you how to fix it. So today we are going to touch upon a more complex problem. It's also a good example for showing the capabilities of the VPSC code. We are going to be looking at zirconium and twinning in zirconium. Zirconium is already complicated because it has several deformation modes that have different characteristics, and in addition it also has tensile and compressive twins depending on the temperature at which you test. So there are two subroutines in VPSC that deal with twinning. One has the predominant twin reorientation scheme, the other has the volume fraction transfer scheme, and you choose which scheme you are going to use when you run the single crystal file. And then there are some statistics done on the Schmidt factor of twins and the twin variant, which are output in these two files. There is one file because the code can run a multi-phase material. You are able to run, for example, a phase. Let's say you can run a polycrystal that has a certain fraction of FCC phase that doesn't twin, and a certain fraction of HCP phase that does twin. So within the twinning modes, we separate the mode, so it could be tensile or compressive twins. So we separate by phase and by mode. So there is a statistic for each of those sets. There is going to be a statistics file. We are not going to be doing multi-phase here, but we are going to be using today tensile and compressive twins. So you will see the structure of this file and how to analyze it. So here, this one gets the Schmidt factor distribution. We introduced already the Schmidt factor. The Schmidt factor for the twin is essentially the result shear on the twin divided the norm of the stress. And this is an indicator of which twin may be most likely activated, because the twins with the highest result shear, you expect them to be the ones that are going to be active. It's not always the case, we will see, but that's what you expect. So it is a good indicator to see, okay, to use for the classification of the twins, the Schmidt factor of the twins. And the twin variants are ordered as first, second, etc. by decreasing order of the Schmidt factor. So you have 6 tensile twins and 6 compressive twins in zirconium, And out of these 6 twins in the grain, you calculate the Schmidt factor, and you say the first variant is the one with the highest Schmidt factor, the second is the next one, so on and so forth. So you don't expect the ones that are 4, 5, or 6 to be active, because they usually have much lower result shear stresses applied. We are going to assume, and this is a good assumption, the twins are activated by a shear stress on the twin plane, so the same as slip, except that the twins can only be activated in one direction, but not in the reverse direction. So they are unidirectional. The shear strain, when you activate a twin, instead of different from dislocations, where the dislocations you emit them in different planes, and essentially they run, and they may even run out or to the grain boundary or recombine. The propagation of a twin involves the growth of the twin. It's not like dislocations that they run on different planes and disappear or interact like that. The twin reorients the crystal, and the twin reorients the crystal and form a lamella inside the grain. So this is the case here. This is a zirconium EBSD, and some of these twins are indicated here in different colors. As you can see, when the twin is activated, the crystal can reorient the z-axis by as much as 85 degrees, practically perpendicular. This is the tensile twin, or in the case of the compressive twin, by 64 degrees. These two other twins are rather rare, so we are not going to consider them, but we are going to consider this tensile twin and this compressive twin. Now, if the twin is treated as a pseudo slip system, so we use the same law, we calculate the shear rate contributed by the twin, and we calculate the shear rate multiplied by delta t gives you a delta gamma of twinning. So for these domains to contribute a certain delta gamma, there is a certain volume associated. The more delta gamma they contribute, the larger the volume has to be. And the proportionality constant is what is called the characteristic twin shear S. The characteristic twin shear S is listed here. For these two twins, is a relatively small number, 0.16 and 0.22. What that means that in order to accommodate a delta gamma of 0.1, you really need to have if this number is 0.2, if this number is 0.1 and this number is 0.2, that means that that delta V has to be 0.5. So if 50% of the grain volume has to be involved, if you are going to accommodate shear with a twin. So that means that there is a limit to the amount of shear that you can accommodate by twinning, because it involves a very large volume fraction usually. So how do we model twinning? Well, I'm going to describe 3 different ways of in which we treat the modeling of twins. The first one is the predominant twin reorientation scheme, which we proposed many years ago. Which here I show the crystallographic orientation between the twin and the parent grain at 85 degrees. So the way that this scheme works is VPSC identifies the most active twin system in each grain. So the twin system with the highest shear or shear rate, which is given by the calculation. The calculation calculates over all the systems a shear rate, and it identifies which is the twinning that has associated the largest shear rate. So you are going to assume that is the predominant twin in that crystal, and you are going to accommodate the formation. You are going to reorient that twin. So what is done is as the volume fraction associated with that twin is growing, as shown here, at a certain point there is a criterion that decides, okay, now this grain is going to be reoriented and given the orientation of the twin. So you replace a parent grain by the related twin, the related predominant twin. So crystallographically the code switches the orientation of the parent to the orientation of the twin. The main reason for proposing this is that at the time when we did that, it was not a good idea to keep increasing the number of orientations. So this keeps the number of orientations fixed. You just replace the parent by the twin orientation, and you continue your simulation. You will see that the effect of twinning on texture is very strong, because you have these huge reorientations that are discrete rather than the gradual ones that happen when you have sleep. Now the second scheme is called the Monte Carlo scheme. It is actually a variant of the predominant twin reorientation scheme. So we are still going to replace the parent by a child orientation, but the criterion for doing so is probabilistic. So instead of picking always the twin that has the highest shear associated, we assign a probability to all the twin variants, which is proportional to their shear. So if the probability is proportional to the shear, the predominant twin has a larger probability of being picked. But when you throw the dice, and that is why it is called a Monte Carlo scheme, when you throw the dice may tell you that you are picking a twin that doesn't have that is not the predominant one. So that gives you more dispersion in the twin activation, and it also accounts for the fact that in reality, when in reality there are local fluctuations that control the nucleation of twinning, which we don't take into account in VPSE. In VPSE, we have a uniform stress in the grain. But there are local fluctuations at grain boundaries that can nucleate twins that are not of the first variant, because those stresses have little to do with the average stress in the grain. And so they may nucleate a twin that is another variant, and then you can propagate that twin. So in a way, indirectly, this Monte Carlo scheme takes into account that, and it gives you more dispersion in the selection of the twin system that you are going to use. Finally, the volume fraction transfer. In this scheme, you identify the predominant twin inside the grain, but then what you do is you transfer the volume fraction of twinning to a new grain with that orientation, with the orientation of the twin, but you keep the parent, except that now the volume fraction of the parent is less, the sum of these two volume fractions is the same, so, and as this twin keeps growing, keeps being activated in this grain, the parent shrinks and the child, the twin, grows. So yes, the shape of the grain, you always treat it as ellipsoidal. We have played some games with this. The games that we played, they don't really give you huge differences, but we have played games like saying, okay, if I have a grain like this, and if I have those twin systems crossing the grain like that, so the grain is oriented like this, the twin system is oriented like that, and we call this a composite grain model. So what we did is when we created the twin, we said, okay, now the parent is going to have this shape, ellipsoidal, and the twin is going to have this shape, also ellipsoidal. So we redefine the shape of the parent and the shape of the twin. But to tell you the truth, you can play many games, but when you look at some real twin structures, sometimes they are not so clean as this thing. So sometimes you have two or three twins inside the same grain. So it is better to stay away from those things unless you have a good reason for doing it, and just you can assign a shape to the twin when you create it. That's not a problem. But as I say, in principle, you can treat it as a new grain that is spherical. Let's say. The truth is, there is no interaction between that twin and the grain. Once you created it, it's like it's like a child. After some time, they leave the house and they are independent. So there is no connection between one and the other. No. So by doing this, you can do this just by picking the predominant twin and doubling. This doubles the number of grains that you need to use, because each parent can have one child, as in the old times in China. No, now that has changed, and But we have also tried that each parent can generate 6 children, and but that means that if you start with 1,000 atoms, 1,000 grains, you have to consider that you are going to have 7,000 grains, because for each parent you are going to have 6 possible children. So your number of grains increases substantially if you do that. But I mean, it is doable. It is doable. As I said, one can play computational games with these ideas, but at the end of the day, one has to be very careful that one does not introduce biases in the calculation, or that you are paying too much attention to this issue and you are not paying attention to other more important issues that have to do with the dynamics and the kinematics of twinning. No? So all these 3 schemes are available in VPSC, and they are handled by those routines that I mentioned before. So the problem that we are going to be tackling today is the one in example 8, is twinning and anisotropy in texture HEP zirconium. We are going to simulate stress-strain behavior and also the texture evolution of an initial piece of zirconium that was rolled. So it has an initial texture. I'm going to show it in a moment. The formation is going to take place by slip in the prismatic systems. There are 3 prismatic systems in the HEP crystal. By 1/1, 1/2, pyramidal slip, C plus A slip. There are 12 systems. 1/1, 2 tensile twins, and 1/1, 2. Oh, this is wrong. I mean, don't. I cut and paste this. This is not correct. I copy the same one, but compression twins. Okay, we are going in the example that I'm going to run today. We are going to treat to use the Monte Carlo scheme in the distribution of the code that you got. All the 3 variants are provided. Today we are only going to do the Monte Carlo variant. Fortunately, the differences between one model of twinning and the other is not so large. So if it was large, then you start really getting worried about the validity of those models. No? So the initial texture is a rolling texture of zirconium. It has been clock rolled and annealed. It has a strong basal component, and now we have to adjust Voce hardening parameters for 4 systems. We have 4 different modes here. So they have different Voce parameters, and we need Voce parameters for each of them. So that is a more complicated task, and that is why I like this example, because it really opens up the field. No? So this is the material that we are talking about. This is the initial texture. This is the normal direction of rolling, the center. But because this material is clock rolled, they roll it, and then they turn it a bit around, they roll it again, they turn it a bit around, they roll it again. And so by doing it like that, they end up with this axisymmetric texture. That was the purpose of doing clock rolling, trying to make the texture as axisymmetric as possible. So these are the basal poles, these are the prismatic poles, perpendicular to the basal poles. As you can see here, the z-axis is perpendicular to the plate. This is the normal direction, or the z-axis is parallel to the normal direction. So the normal direction of this material is going to be hard. The normal direction is going to be hard. So if this is the z-axis, these are the prismatic planes, and the twins I'm using are the ones on this plane. This is the Burgers vector. This is the Burgers vector of this plane. In the prismatic plane, this is the Burgers vector. So this twin provides deformation along the z-axis, but only in tension, not in compression. But that is why we have the pyramidal system that can provide both in tension and compression. So, but the compression twin will provide deformation in compression. But you can already see that the yield surface is going to be anisotropic. because things are going to be different in tension and compression. So what you see here is the result of doing 4 tests. Actually, we could only do 3 tests because the plate was about 1 centimeter thick. We couldn't really do good tensile test in the normal direction. We tried, but we failed. So we did only test but with a computer you can do it. So with a computer that's not a problem, and we did it. So if you do in plane tension means that you do tension along this direction in the plane of the plate. You get this curve. If you do in plane compression, you get this curve. If you do through thickness compression, you get this curve. And if you do through thickness tension, you get this curve. As you can see, the material is very anisotropic. Not only that, but gives very different results in tension and compression in the same direction. So that is an interesting material to model. The Voce parameters that we are going to use are listed here. There's no need for you to read them, but you can see that the prismatic is very easy. It has relatively low Voce parameters. The pyramidal has very high Voce parameters, and the tensile twin is somewhat in between, and much easier to deform than the compression, to activate than the compression twin. There is this, which are the latent hardening parameter. You remember yesterday we were talking about the delta tau, d tau, d gamma, sum h, s prime, delta gamma, s prime. Those are these parameters. So those parameters, as you can see, they are not all one, and the main reason has to do with they are empirically obtained, but the interpretation of why these parameters are large in some cases is because the presence of the twin will tend to harden the slip systems. They are not really hardening the slip system. They are putting barriers. They are putting barriers to the slip system that look like you are really hardening. It's much difficult to activate those systems because of the barriers that the twins put inside your grade. So the exercise that we're going to do is, just the in-plane compression at 76K. The reason for using the parameters at 76K is because at that temperature, both tensile and compression twins are active. At room temperature, the compression twins disappear in the zirconium. So only the tensile twins remain. And past about 150 degrees C, that is 450 K, also the tensile twin disappear. And the reason for in general, the twins disappear with temperature, and it's not that they harden with temperature, but it is because the slip softens with temperature. And so, as if slip becomes easier and easier because it is a thermally activated mechanism, the twins have a relatively flat critical stress, but the slip systems have a strong dependence with temperature. As the temperature increases, the critical stress to move them is easier and easier. So the reason for the twins to disappear is because the slip is much easier in general in all materials at high temperatures. This file, this is called VPSE8 MC for Monte Carlo.in. It will have to be copied into the root directory as VPSE8.in. We are going to do 20 steps of 1% strain, and we are going to calculate the final yield surface at 20%, the p-plane projection of the yield surface. So this is the VPSE file. Only the lines that matter are copied here. This is the file that we are going to be using for a single crystal. This texture is the texture that I showed before. So we have 2 processes in this simulation. One is uniform strain rate, in this file in plane compression 20% in the direction 1, and then the next process, type 2, which is the calculation of a yield surface, and the components of the yield surface are going to be the components sigma 1 and sigma 2, which is the p-plane projection of the yield surface. Yeah, I know what you mean, because this morning I noticed that that directory is not there, but what you have is BPSC 8 PTR.in. Actually, this is misnomed. It should be MC. it should be MC.
Ah, okay.
And the only difference between those two files, is that is two numbers. That the PTR is assigned an identification 1 for the twin system, and the MC is assigned an identification 2,
Ah, okay.
and the volume fraction transfer is assigned an identification 3. So if you look at
Okay.
the end, at the very end of the single crystal file, no, we are looking at the single crystal file, not the ZR 76K MC single crystal. You don't have MC, but you have PTR, I think. I think that's what, let me check. So you went to IPC 76K. I don't want that. Yes, there is a VPSC, BFT, PTR, and there is a VPSC, BFT and PTR. I think that PTR, let me, yes, as you see, the VPSC, PTR, 8, PTR, dot in, in reality, if you look at what is listed there, it goes to look for the MC single crystal file. It goes to look, so it is mislabeled. This file should be labeled MC. That file should be labeled MC. Yeah, I need to fix that in the distribution version. But it contains the MC. It points to the right Monte Carlo, but it's mislabeled really. Now this is what the single crystal file looks like. It is wrapped around because it's too long, and I only included one system per mode. But it's a good occasion for showing you how you use many different modes. So you give the aspect ratio of the unit cell and the angles. Observe here the 120. The two basal axes are separated by 120 degrees here. That's the difference. And this is the C over A ratio. As I said before, you don't need to put the absolute values of the lattice parameters. You can if you want, but with putting the ratio is enough for the crystallographic calculation. Then this file has 6 systems, 6 modes, which are the prismatic, the basal, the pyramidal A, the pyramidal C plus A, tensile twins, and compressive twins. Of this, we are going to use the mode 1, 4, 5, and 6. So we are going to use prismatic, pyramidal C plus A, tensile twins, and compression twins. The twins have an extra number. You give an extra number, which is the characteristic shear of the twin. Here, the twin shear X. This is the characteristic shear of the twin. And there are 6 tensile twins. There are also 6 compression twins, and this is the characteristic shear of the compression twin. Now, you wrap around, you go to the constitutive law. So we are going to run a Voce law. The grain size doesn't matter because we don't have whole page coefficients in this law. Actually, yes, we read a whole page coefficient, but it is zero. It is zero for all the systems. And then these are the Voce constant, tau 0, tau 1, theta 0, theta 1, and the HSS prime coupling the different modes. This couples the prismatic with the prismatic, this couples the prismatic with the pyramidal, this couples the prismatic with the tensile twin, this with the compression twin. This one will, for the pyramidal, couples the pyramidal with the prismatic, the pyramidal with the pyramidal. Imagine a matrix. you have prismatic here, you have pyramidal here, pyramidal here, you have tensile twins here, you have compression twin here, you have tensile twins here, you have compression twin here. So this is the H prismatic, 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 prismatic. This is the H prismatic pyramidal. This, for example, will be the H tensile twin, etc. And it is the same for all the modes. This is mode per mode, not system per system. As I said yesterday, if you have a good reason to make them different for different systems, you can populate this matrix, which is 3, 12, 6, and 6. So this is 24, 27. This is a matrix of 27 by 27 systems in total. You can populate them with different H's, but it becomes a nightmare, of course. You don't control what happens anymore practically there. So coming to the twinning systems, here you can see that these numbers have a meaning. The secondary twinning, which has a 1 means yes, 0 means no. So 1 means that yes, we are going to allow for secondary twinning. So we are going to allow for that in the twin we are going to allow for creating another twin. This 2 refers to the twin law. So this is the Monte Carlo. This is the Monte Carlo, the 2 that I was talking about. So this is 1 for the predominant twin orientation, 2 for Monte Carlo, and 3 for the volume fraction transfer law. And these 2 numbers really are 2 thresholds. We don't allow for twinning until 10% of the volume of the grain has been compromised. We don't activate the twin right away, except for the volume fraction transfer scheme. We start early. So this is the in-plane compression, 20% in the direction 1. There's nothing strange here except that now we are putting a strain rate epsilon dot 11, which is 10 to the minus 10 to the minus 3. These 2 numbers don't have much of a meaning because we don't know when we compress our sample how it is going to deform laterally. So you have to put something there so the code has something to get started, but they don't have any meaning because these 2 components are not imposed. As you can see, these are zeros. These 2 components are not being imposed. On the other hand, you do impose sigma 22 and sigma 33, and you impose them to be 0. So it's a compression. There is no stress laterally. As I say here, the final state, if you leave these components free, you allow for ovalization of your sample. If the sample wants to become oval instead of remaining cylindrical, it will become oval, and they do. So this is the kind of results that you get for all the 4 cases. We are going to run here only the in-plane compression case, or maybe a couple of cases. So these are the results that you get both for texture and for activity. First let's look at the texture, which is the easier to analyze. These are the basal poles. Your basal poles are along the normal direction mostly. And when you do in-plane compression, that is, you do compression along this direction, what you are doing is you are putting your z-axis in tension. So you have here your hexagonal crystal. If you do tension in this direction, the deviatoric component, which is the one that matters in plasticity, gives you, if you do compression here, it gives you tension in this direction. And tension in this direction will activate the tensile twins. If you do compression in this direction, if you do now tension in this direction, now, the deviatoric is going to go in the opposite direction. There's going to be a compressive here, but that compressive is not going to be enough to activate the compression twin, and you will activate mostly prismatic slip, which is very well oriented, the prismatic slip, because this is the Burgers vector of the prismatic slip system. It's very well oriented to accommodate this deformation. So in plane compression, you activate tensile twins. The tensile twins flip the grain in the direction of by 85 degrees, and so after 20%, you build up this component. you build up this component, this basal component, because the z-axis flips by 85 degrees towards the compression axis. If you do in-plane tension, practically nothing changes. This is because you are activating practically 100%, accommodating it practically 100% with prismatic slip. Well, not fully rotated by 90 degrees, but ideally 85, but it's not fully, you still have a component here. You still have this component here, but if you keep pushing, probably, if you do it in magnesium, magnesium is even twins even much more easily than zirconium, and you can reorient practically the whole grain, all the grains, or 90% of the grain you can reorient and change completely the texture with relatively little strain. No? So as you can see, here is all prismatic slip. There is nothing of the other system, no twinning. In the in-plane compression, we have a lot of prismatic slip, but we also have the green line. The green line corresponds to tensile twins, so we are accommodating the formation with a substantial amount of tensile twins. Here, the green. And then the blue is some compression twins. Red is the pyramidal remains flat. The pyramidal is not being activated. And this is interesting because these compressive twins, you wouldn't expect the compression twins to be present for this type of texture. Because you are doing compression here, as I said, you are doing compression here, you are putting a deviatoric tensile stress in this direction. So there are no grains really where the z-axis is going to be in compression. But when you start twinning and developing this component, so the grains twin, and now they reorient to this orientation. They reorient to this orientation. Now this orientation is going to have z-axis aligned with the compression direction. And then you are going to start activating compression twins. So do you remember that I talked about I secondary twinning equal 1? So if you allow for secondary twinning, what you do is you allow for a piece of the material, a fraction of the material that has twin, you have created a new grain that is the twin grain. But if you are allowing for secondary twinning, then that grain is going to twin again and bring this somewhere here, more or less. So that is one of the effects of allowing for this I-secondary twinning there. So what you are doing, and the compression twins, they do not start until you have already built up some amount of tensile twinning. As you can see here, the compression twins, which are the blue line, they start at about at 10%. So at 10%, you have already a volume fraction of tensile twins. You have a volume fraction of tensile twins of about maybe 25%. This is the volume fraction of tensile twins. It's 20-25% of the material has tensile twin. And then you have some amount of compression twins. It's not a big deal really. Are these red squares. Now here nothing. In the through thickness compression, you are compressing the z-axis, you expect to activate compression twins, and that's what you see here. You see a lot of the blue, at least at the beginning. You have a lot of the blue systems, which are the compressive twins, being activated. The prismatic is always activated because the prismatic is easy. So even if the Schmidt factor is small, they don't need much stress to get activated. Now, in this case, the compression twins grow to be about nearly 50%. 50% of the material has twin by compression. But once again, the same story is true. When you activate the compression twins, the twin itself puts the z-axis in favorable for the tensile twins to be activated. And so then you have compressive, but you also have tensile twins being activated. Finally, when you do through thickness tension, you are pulling in this direction, so you are going to be activating tensile twins because the pulling is parallel to the z-axis, and that's what happened. You practically deplete the texture. All this component is depleted and is sent to to the edges of the pole figure, because it reorients by 85 degrees. Well, as you can see, in through thickness tension, you start with a lot of tensile twinning and some prismatic slip. The reason you activate prismatic slip is that if you look at the initial texture, it has grains that not all the grains are at the center. You have grains that are here, so they're inclined, and so some of them are inclined far enough that the little result shear stress that you put on those prismatic systems is going to activate the prismatic, because the prismatic, as I showed before, is like 5 times more favorable than the other systems. So that's the explanation. But as you can see, it is a complicated interplay. There is a complicated interplay between the modes that you activate, and when you throw twinning into the equation, then things get even more complicated, because now, as you are deforming, your texture is changing in substantial ways. So all that interplay really gets very complicated, and I always say that sometimes I am marveled by the fact that we can predict anything, because when you look at the real material looks very messy, and with these simple models, you can predict things. So I mean, you can predict up to a point. There is a lot of micron size scale things that you cannot predict with this model, but texture and stress strain response, they come out fairly reasonable. So sometimes I'm surprised that that's the case. No. The next thing that I wanted to do has to do with this analysis that we have done in the previous slide, but is for you to understand and be able to interpret the activity file. Now, this is the activity file for this problem. You remember, for the cubics, it had only 3 columns, the activity file. Essentially, it had the strain, average number of active systems, and had a column for the contribution of each mode to the formation. At most, it had 4 columns when we were dealing with the BCC materials. It was the activity of one of the slip systems of the BCC and the other slip system of the BCC. Now here we have 4 modes. So we have mode 1, mode 2, mode 3, mode 4, which is prism, pyramidal, tensile twins, and compression twins. And it also lists the amount of primary twinning and the amount of secondary twinning, what we were talking about before, the secondary twinning thing. So what are the volume fractions? And I'm coming to this in a moment. So first, you can see that for this particular problem, for IPC, you start with 98% of the shear is coming from the prismatic system, very little in some from the tensile twin. And as the formation proceeds at 20%, the prismatic system is contributing 71% of the shear. The pyramidal, only 3%, very little, is too hard. The tensile twin is contributing 13% of the shear at that point, which is noticeable, and the compression twin is contributing 12% at the end of the formation. These are instantaneous contributions. These are not accumulated. These are the rates at each step. On the other hand, the primary twins, that is the twins that you created first, the children, are increasing in volume fraction to become 49%, and the secondary twins, that is the grandchildren, are about 1%. So no, not too much really, because that means that the grain that has reoriented, you clean that grain from the previous history, and you deform that grain as if there is no previous history except for the hardening. You just keep the hardening, but you clean the twinning history, so it's clean from twins, that new grain, and then you start treating it in the same way, and if it twins again, then you consider that secondary twinning. These two quantities are important, because this is the twin fraction of the tensile twins, system 3, and the effective fraction of the tensile twin, and the same for the compression twin. I come to explain what those 2 columns represent. We said that if you have a shear rate in the twin system times delta T, divided the characteristic shear of the twin, that gives you a delta F or delta V for that twin. That is a kinematic relation. So so the volume fraction over the polycrystal is the sum over all the grains of delta V twinning in each of the grains is going to be the sum of gamma dot T in the grain delta T divided the characteristic shear, which is the same for all the twins. So this volume fraction means is for all the twin systems. Oh, sorry, and there should be a sum. There should be a sum over the grains and over the twin systems. There should be a sum over the twin systems. So this is the volume fraction that you actually measure if you do EBSD, that you see in an ABSD image if you measure the volume fraction of twins, because it's kinematic, it's associated with the shear accommodated. But what we are doing with twinning is we have a criterion to decide when we flip the grain. So we reorient the grain. We call this is what we call the effective twin fraction, what do they call it? The twin fraction. We call the twin fraction. But the effective twin fraction, is the sum of the grains that have reoriented, the sum of the weights of the grains that have reoriented, because you reorient the whole grain. So in principle, you want to keep these two things as close to each other as possible, because this is the real thing. But in your model, you just flip whole grains, so you don't want to flip in excess the grains. So there is a criterion inside those twinning subroutines that what you do is you pick your grains at random, decide if that grain is going to be a candidate for flipping, and then you flip it, but you flip it in such a way that you stop when this quantity is equal to this quantity. So you don't want just to keep flipping grains. So you want that the grains that you flip represent the same volume fraction that of twinning that as the one that you would be measuring when you do an EBSD test. And so there is a criterion, and as a matter of fact, if you look at how these things change, I mean if you and those are those two columns that I was putting there. This would be the twin fraction, and usually the effective twin fraction is something that starts a bit low, but it meets the other one, and you can see that in the output file. That is what is happening. So here the twin fraction here, for example, is, of course, there are some steps missing here, some increments missing, but here is 0.17, 0.017, 1.7%. This guy is much lower, but we're talking about small numbers. But when we are getting to the end of the formation, this number is 0.43, this number is 0.43, this number is 0.45, this number is 0.45. this number is 0.47, this number is 0.47. So the criterion is such that you stop reorienting grains when those grains, by being reoriented, will be exceeding what it should be there, the actual volume fraction of twinning. Yes.
Is it like when a particular fraction of the grain twins, then we decide to change its orientation because of the twinning? Is that the kind of criteria that we are using?
When the particular fraction of the grain.
So there is twinning in a particular grain, and beyond a fraction of the grain, if it twins, then we decide that we will assign a new orientation to it as a result of the twinning.
Okay, I'll explain what the algorithm is. That algorithm is inside those subroutines for twinning that I mentioned before. I'm going to explain how it works. So let's assume that you have a certain number of grains here. And that you have calculated that this grain has a certain volume of a twin being activated. This grain has. So this is the volume fraction of twinning for the grain 1, grain 2, grain n minus 1, grain n. Okay. So you go and you sample and I define two thresholds. Those thresholds are, you can change them. I define a threshold 0.1 and a threshold of 0.5 there in the single crystal 5. What these thresholds do for you is that the criterion, the volume fraction threshold is equal, let's call this threshold 1 and let's call this threshold 2. So the volume fraction, you define a volume fraction threshold, which is threshold 1 plus threshold 2 V V twin fraction V effective over V twin fraction. So at the beginning of the formation, you haven't reoriented any grain, so this is 0, okay? And this number is going to be 0.1. Then you go and you sample all your grains, your 500, 1000 grains, whatever. You sample them randomly and say, okay, maybe you pick this grain and you pick this grain, for example. And you say, is this volume fraction larger than the threshold? So if the answer is yes, then you reorient the grain. And the threshold at the beginning is 0.1. So it has to accumulate at least 0.1 of the volume fraction of the grain to qualify. Okay? You may check this one, and you check this one, and if the answer is no, you just keep throwing the dice until you check all the grains. Okay? But then you have reoriented a certain number of grains, which means that this number starts increasing. And what happens is, as this number starts becoming close to the actual volume fraction of twins that you measure, let's say, this number is going 0.5, and this number is going towards 1. It's going towards 1. So you keep increasing the threshold, you keep increasing the qualifying condition for a grain to be flipped. And so you stop flipping grains when you start exceeding, when this guy starts exceeding this guy. So I don't know if that explains your.
Yeah, but
I mean,
one more.
there are details, but that's the idea. The idea is that the threshold is a moving target, but that just keeps increasing.
Right. So one last question. So
No, go ahead.
the values of these constant TR1 and TR2 that determine this equation. So those values itself will be calibrated with some experimental measurements, or
Yes and no. I can show you a plot that we make the well. I can show it. Well, no. I can show you a plot later that shows that it doesn't really matter what you put here because it matters to some extent, but not too much. Because what really matters is that this criterion keeps these two quantities more or less and equal to each other. So at the end of the day, I mean, it doesn't really matter when you start flipping your grains. So if you start flipping late, this is going to start here, but it's going to go there. If you start flipping early, this is going to go here, and then it will approach it there. But at the end of the day, it doesn't really matter much. The model is not very sensitive to those values.